So let's say we have some function. We're going to call it f of x. We have our x-axis and our y or function axis. And just like any function, for some value in x, let's say c, we'll call it. Why not? We're going to have a function value of the function of that point, right? F of c. That seems perfectly normal, right? That's the whole idea of a function. When we get closer, when we get to this point here, c, we get some point f of c. That's what a function says, right? But what if we have something slightly different? What if we have a function that has a point missing? There's something wrong with this function. Look, it's got this point. It's got this point that's just out of the function. It's way up here when the function is going like this, but there's this one point that's way up here now. Now that doesn't look right, does it? It looks like there's something terribly wrong with this function. And this can be thought of as a piecewise function. This might be that we have f of x or y is equal to, we'll say, some function of x, except the y is equal to what we can call this some point, I don't know, j. Y is equal to j when x is equal to, what's this point here? We'll call it c again. When x is equal to c. That's how you think of this in a piecewise sense. So how can we think of this function? Because there's clearly a bit here. There's this bit missing, right? I drew it as a little circle there to show that something had been like taken out of it, but really there's just a point on which the function isn't defined like that. It's defined by this point j. But as we go deeper into other studies, especially calculus, the idea of this point here, this point that's missing, will become pretty important. And here's where I'm going to introduce something called a limit. Let me write that out. I can't really write cursive. A limit. Now, a limit is this idea that kind of seems obscure the first time you learn it, but will come to make more and more sense as you go on. A limit essentially discusses what that missing point is, what our missing point is, or not necessarily missing point. It's really just what our function of x is approaching as we approach c. So how can we diagram that in a good way? So as we get closer and closer to c, like c plus 1 or c minus 1, we're going to have these other points on the function, right? For our old function and for our new function. We get these other points. But you'll notice as we get closer and closer, these points converge on this one point here, or this missing point here. We can get closer and closer, so close that the points almost become the same points and represent this thing here. But we can never reach there, right? We can't just plug in c, because that won't give us our missing point. That'll give us this thing. So we use this thing called a limit. We write it the limit. You might see it written cursive. And we say as x goes to c of our function, right? Because we're looking at this function and we see as we scoot our x's closer and closer to this one point that we want to find the missing point for, or the real point for, right? We can do the same thing here. There doesn't have to be a missing point for this. As our x values goes to c of f of x, we're seeing as we get closer and closer to c, what does our function get closer and closer to? It's kind of seeing as our x value converges to something, what does our y value converge to? And here, you'll notice it converges to this missing point here. And how would we define this missing point? Well, if you look at the other graph, I mean, at the other graph, it's pretty clear what this missing point is. It's because it's not missing. As we get closer and closer to c, our function gets closer and closer to f of c. And that's going to be equal to our limit. But over here, f of c is not our value here. F of c is way up here. We don't really care about this. This is not really what's important. You can just randomly make a j. But this missing value is what we're trying to find. So the limit, as x goes to that, well, you can just look over here, right? Why would it be any different? All we did is take that point out. If the point was still there, we'd be converging to f of c. That's what we would become. So that's what we're getting closer and closer to. Though for this function, we cannot just plug in c and find the function value. We can say as we get closer and closer to c, we get closer and closer to the function at this point. Not some j, but the function at this point, f of c, which is said not to be defined in that way. But that's what we're getting closer and closer to, right? What point did we take away? It's pretty clear. But it's not always clear. We're going to look at another example. So what if we have the function sine of x divided by x? This is our function. All right, let's try to graph this function, because you'll look at it and there's a pretty clear problem. What happens when x is equal to 0? Okay, that means we have f of x, or f of 0, is equal to the sine of 0 divided by 0. Okay, first of all, we're dividing by 0, okay? Second of all, this sine of 0 is equal to 0 itself. And I'm going to be talking about this more in other videos, but dividing 0 by 0 is a unique problem in that it discusses ambiguity. It's not undefined exactly. It's ambiguous. And what that means is, think about the definition of division. If A divided by B is equal to C, then A is equal to B times C, right? That's just algebraically, this is how we divide. So this is true, but then A equals B, C must also be true, right? If we say this is true. So what if we take 0 over 0? We take 0 divided by 0 is equal to, I don't know, 5. Why not? Then that would mean that 0, right, A, is equal to B, which is also 0, 0 times 5, which is 0. That's true. That would be true if we chose any value, right? If we say 0 divided by 0 is equal to L, just some random L, then that it follows that 0 is equal to 0 times L. So that's always going to be true. So 0 divided by 0 can be really equal to anything. There's no way there's no way to define it. It's not that it's undefined necessarily, but it's defined as too many things, so it's meaningless. So obviously we have a problem here. But what if we try to take the limit? What if we see as our x values get closer and closer to 0, as we get closer and closer with our x values to the origin, what will our function get closer and closer to? And I encourage you to try this with a calculator because it's very interesting. Just plug in values of x to sine of x over x that are smaller and smaller and see what they're getting closer to. But I'm going to graph it for the ease of that. So if you graph sine of x over x, you get this kind of interesting curve here. Wait, there's a problem there. I looked on a graphing calculator, and this is what you'll get. This curve kind of like this, where you start in the middle, you're above the x-axis, and the sine curve gradually gets smaller and smaller, which makes sense as x gets larger and larger, be it negative or positive. You're going to be dividing by a larger number, which means your function is getting smaller. But you'll notice there is a point here. It's missing. But we can't just say, oh, right, the limit there is not So we're going to say the limit as x goes to 0 of this function f of x is not equal to, well, it's not equal to f of 0 because f of 0 can be a bunch of different things, but this is only one thing. So maybe, you can say f of 0 is equal to this value, but f of 0 is also equal to a bunch of other things, so it's not meaningful to say that. But what is this point? What is this point we're getting closer and closer to? Because that seems like an important point. That there's a trend. There's a trend in this function that's leading to that one point. And as we'll see later in calculus, that's a really important idea for some other concepts. So let's try to define this limit. Well, I can just tell you from looking on the graphing calculator, or if you have a calculator on hand, just trying to do it with the calculator, that this point is going to be 1, this missing point. If you plug in smaller and smaller values of x for this function here, you get closer and closer to the value 1. But you'll notice, we cannot just say, oh, it's just the function at that point. It's not like we just put it up here, right? We didn't just say, oh, let's just take out the place from that function there, right? The function isn't actually defined there. So that's why the idea of limits is kind of useful, because you can't simply it's not just about taking out that one point. Sometimes the function's not clearly defined at a point, and a limit is the only way you can describe that little issue, which we're going to learn is called a discontinuity. I'm going to write that out. A discontinuity is the name for these issues, these little problems where the function isn't quite as it should be. So what's really the difference between a function with discontinuities and a function with continuities? The difference between these two functions, one that has a discontinuity here, a discontinuity that actually has a special name because there are different types of discontinuities. This discontinuity is called a removable discontinuity. So what's the difference between this and this function? And now you'll see our first application of limits, right? No discontinuities. What's that? A normal function with none of these problems has no discontinuities? Well, we can call that a continuous function. A continuous function for which all the values of x have a proper value of f of x that is defined, right? We have some f of x, and we have some value x. And this is continuous. It has no points at which something went wrong. And what did we learn earlier? The limit, as we approach any value, let's call this x now, it could be c, it doesn't matter. We'll call this x sub c, doesn't really matter. We approach some y value, right? As we get closer and closer, we get closer and closer, right? As we get closer and closer, we get closer and closer to this one value, and that's just going to be f of x sub c, right? As we get closer to this point, on our function, we do get to this point, and that's the actual point on the function. This is the actual point that we have. It's defined. So the limit, how are we going to define this? The limit, oops, the pen does not want to write. There it goes. We're going to say the limit of our function f of x as x gets closer and closer to some value. Well, let's call it, well, we already used x sub c, so why not, is going to be equal always to the function at that point. This is our definition of a continuous function. So when you see a function that has no issues with it, this is how you can formally define that. The limit, as you get closer to any point on the function, is going to be the function defined at that point. So the limit here, there's no removable point. The limit here is what the actual point is here, right? That point's still there. So as we get closer and closer to that point, we can actually reach that point. As we get closer and closer along the x's, we get closer and closer along the y's to the point that's actually defined, that's actually there. Whereas on the other one, that's not true. It's the function that's meant to be defined at that point is actually way up here. That's not the limit. As we get closer and closer to some value, x sub c, we get closer and closer to this value here. This is the limit. The limit, this isn't proper notation, but it does for now. Our function is actually up here. This is our function of x of c, whereas our limit is something else. So when you have a continuous function, the limit as x approaches one point is the function at that point, whereas with a non-continuous function, that is not true. Thanks for watching.